class, so I'm glad everybody's able to be voting. I'm glad those of you who showed up. But today, it looks like most people have to be other places. So I'm just going to record this, and then it's posted, and on Thursday we're moving on to digestion. So here's the last little bit of respiration, and the first part of respiration. Sorry, not respiration. Last part of respiration, first part of digestion. But we totally still have lab today, so that's good. When we look at the respiratory system, there's the tissue level stuff, right? Of you're needing to have gas exchange across membranes. You're needing to have bulk movement of air in and out, the whole bit. Where we are now is how do you get that bulk movement of air in and out of the lungs, right? So this is going to happen because pressure changes. So you're going to be changing the pressure in the thoracic cavity, and that's going to make gases flow in and out. So we're going to look at this in two steps. There's inspiration, which I realize sounds like a motivational poster, but it's just air is coming in. It's the flow of air into the lungs, inhalation. And then expiration is exhalation. It's when air leaves the lungs. So when inspiration happens, when you're pulling air into your lungs, your diaphragm and some of your rib muscles, your external intercostal muscles, they're going to contract. But as they contract down, it pulls the thoracic cavity open. And this is going to suck air into the lungs. And I have my handy dandy little model here. I hope you can see this appropriately. What happens, and I realize there's a lot more to it than this. This is a model that you all were working on making last week, but I realized the bottles were a little bit squishy, so sorry. But as your diaphragm and also some rib muscles, but they're not modeled here, as those contract, you physically make there be more space inside the cavity. So the space is bigger, but if there's a certain amount of gas in a specific spot, this it's called the interpulmonary volume. If that volume gets bigger, but the total amount of gas stays the same because it's not open to the air on the inside here, the pressure drops. So the pressure inside here is going to drop because suddenly you get bigger, and then air, if this red balloon is supposed to be the lungs, air gets sucked into the lungs. So it might be mostly deflated right now, but as we contract the diaphragm and make there be a larger space inside, we'll pull air into the lungs. We'll suck it in. Make sense? There's not actually a muscle here that we're worrying about. We're worried about changing the pressure in the thoracic cavity. So you'll suck air into the lungs. It's going to look like this. Your ribs are going to go out. Your diaphragm's going to move. You're going to get bigger space. You're going to stretch out your chest. To be fair, people can, like if you put your hands on your ribs, and as you breathe in, you'll feel it get bigger. If you're tricky with your muscles, you can actually breathe in while moving your muscles in. It's not recommended though. Don't do that. This is how the pressure is going to go relative to the atmosphere during inspiration and expiration, right? So inspiration, the interpulmonary pressure is going to drop, and you're going to pull air in. And then, if you're done with that, you don't do it quite so dramatically. As the diaphragm stops making the volume bigger, the interpulmonary pressure goes back up, and air comes out. I don't know if you can see that okay. You're going to pull air in, you're going to push air out. You're going to pull air in, you're going to push air out. And we're not worried about changing the air inside the jar. We're worried about getting air into and out of our little lung here. Yeah, so inhalation, exhalation. During inhalation, it's an active process. You're actually pulling open the cavity. Exhalation, you kind of just let it happen. Muscles relax. Air is pushed back out because there's more pressure. You can also force it. You can, if you want to, just, you're breathing in, you're breathing out. Breathing in, breathing out. You can also force air out. That works. You just contract the internal intercostal muscles to depress the rib cage. What? Normally, in that pleural space, you always have some negative pressure. You want to keep the lung pulled at least open. It can get bigger and smaller, but you want it to at least not be collapsed. Here's a video to watch what happens if you trap. If you get air trapped in there, and you end up squishing your lung down too much. You can also collapse your lung. Both are bad deals. We're gonna just look at one here. This is called pneumothorax. This is when they say collapsed lung. Pneumothorax is where you end up building up air inside the space and it crunches the lung down. You can also collapse your lung if you physically punch a hole here in the chest wall. That's a problem. We're gonna look at pneumothorax. Come on. Breathe.
Hey, so pneumothorax can cause a lot of pain, a lot of anxiety for our patients. So let's...
I have no idea what's happening. Just a sec.
What are some of our treatments? Okay, when we talk about pneumothorax, we're talking about air getting into the pleural space. So here's our lungs. We have our left lung, our right lung. And surrounding that lung, we have what's called the pleura. Okay, the pleura is a little protective covering that surrounds our lungs. Now that's a great thing. It helps protect our lungs. It helps our heart expand. It helps everything with respirations to protection and everything. But what can happen is our lungs can develop these little blebs on them. These blebs are little tiny vesicles of air, and what can happen with those blebs is they can rupture. Okay? And once they rupture, you can imagine that air comes rushing out of our lung and it begins to fill that pleural space. Now there's nowhere really for that air to go other than into this pleural cavity. So what will happen is the air begins to compress this lung down. Okay? The lung becomes compressed as this space fills with air. Okay? So that's what we call a collapsed lung, is this air filling up in here. When it can't escape, it can't get out of this pleural space, so it pushes the lung in. Okay? That's a pneumothorax. Now what do we do with a patient who has a pneumothorax? As you can imagine, it can cause a lot of anxiety, it can cause a lot of pain. So what the physician can do is they can cut a little slice, a little incision here, and they can insert a chest tube. Okay? So the tube will go in right to where that air is collecting within the pleural space, and it will allow that air to come out. Okay? Now when the physician enters that, it really does, it sounds almost like opening a can of soda or something. As they enter that space, and to know that they're in, you kind of get a sound of like cracking open a soda. Tss, and that's that air rushing out, okay? So as we allow that air to come out, the lung tissue then begins to expand again as that air escapes and it releases that pressure that it has on the lung, okay? So this is John with nrsng.com. If you want more free in-clinic...
Okay. Do you see that how you can end up crunching the lung down? It's a bad deal. It's scary, but it can be solved. So it's the lungs being held open by pressure. It's being it's being held up by pressure. It's then also moving air in response to pressure changes. Yeah. Other things, so just with models, and I realized you couldn't do these, I'm sorry. With models, there are a number of different things you could model. You could have modeled, again, if I had given you appropriate models, you could have modeled what can happen if, say, the muscle gets weak or stiff, right? The diaphragm isn't good at its job. Then it can be really hard to move air back and forth, right? Because this is challenging. The lungs can become non-compliant. So you can imagine, you know the thing that happens with rubber bands if you've like left them in the car for a long time and they get kind of like crackly, they're not as elastic. If that happens to your lung, the lung itself isn't doing its expansive job as well. You can also have something happen that fills the lung up with fluid. So you can think like pneumonia or drowning, right? Where if I start filling up here with goo, I can't get enough air in because I've got full of gunk. And there could be a whole bunch of things. You could have a puncture in the side here, and then as you try to move, air just hisses out. You could have problems with the lung itself. Lots of different things you can have a problem with. If you wanted to model something like asthma, you'd constrict this opening quite a bit. So you'd like tie it off with a string or something, where suddenly there's less, like you can still do the pulling thing, but here let's actually just model that really quickly. Where you have some sort of constricted air passageways. Drat. Sorry, I should have put this inside. Give me a second here. So, briefly, with asthma or other things, your lungs don't come out of your chest. But there's a constriction of how air is able to flow. And then, this is more challenging to do quickly than I thought. I feel like I should spend more time doing arts and crafts activities with you all, apparently. Come on, there you go. Okay. Then, as you're trying to, you've got constricted airway, then as you're trying to pull in, you're getting a little bit of air in there, but you're not able to move as much as you normally would. So, things that happen with lungs. I know you saw this in lab, but you're moving different amounts of air in different portions. Normal breathing, you're moving about half a liter of air in and out each breath. It's called your tidal volume, just the amount that moves. Again, if you're bigger, different physical conditions, you can move different amounts, right? So there's an amount you could just normally breathe in and out. You also have an inspiratory reserve volume, which is the amount you can take in addition to your tidal volume. So if you're breathing normally, you can also then pull extra in. There's also the expiratory reserve volume. So this is after you've had this normal about half a liter of air in, out. You can also force more air out as much as you can, right? So you've got reserve volumes both in and out. There's also what's called a residual volume. This is even after you've breathed out as much as you can, there's still air in your lungs. This is going to make it so that, because there's still air there, even as you breathe out, gas exchange still can happen, right? So you're moving air in and out, but there's still some left over, and so gas exchange is still going on with that. Amongst other reasons, this is why even if someone's not breathing, if their heart's still pumping, they're still getting blood to the lungs. That's helpful. And also, you want to keep these the alveoli open and inflated. It becomes a problem if your little alveoli, right, which should be compliant, they should be elastic. If those collapse, if they don't have any air in them, they're closed, and then it's really hard to get them back open again because they stick to themselves. So that's a bad deal. Your vital capacity is just the amount you can exchange, right? So it's your tidal volume, inspiratory reserve, expiratory reserve. There's also what's called dead space volume. That's the air that's in the conducting zone that never actually gets to the alveoli because you have air in the system. It's not a huge deal. The air that reaches the respiratory zone is, of course, less because you have some that's just in the passageways. And then you kind of way to measure this, you basically have people blow into a tube and you watch it. If you want to do it yourself, what you can do is if you want to see like how big your volumes are, you could get a tube and say, again, if we could breathe on each other, we'd do some different things. You could get like a gallon or two bucket, or sorry, like a milk jug, right? Filled up with water, turn it upside down, and have it underwater so that the milk jug is full of water. Put your tube into the jug, into your mouth, and breathe out. And you see how much air you could put into the container, and water will come out, and then you can measure that volume. Spirometers do basically that. They're a little bit more high tech. So different amounts of lung capacity, you're going in and out, things are all good. There are other gas movements that happen that aren't specifically for carbon dioxide or oxygen exchange. Some of these are reflexive, some of these are voluntary. They're things like coughing and sneezing, right? Trying to get rid of gunk in the, sorry, I put air. Sneezes are more typically just from the nose. Excuse me. And so coughing and sneezing, you're trying to get gunk out of the lungs or out of the respiratory system in general, right? You've got smoke in there, or you have mucus, or whatever it is. Get it out. Crying is emotionally induced. So crying, I realize also is the eyes, but if you're like, the air movement is an emotional one. Laughing similar to crying. There's still research on why exactly we laugh. There's a whole bunch of theories. It's kind of interesting. Thinking about yawning is making me yawn. Yawns are very deep inspirations, right? The idea for it is that the body is trying to get additional oxygen, right? So you're kind of falling asleep, or you're really tired, and the thought is your brain says, we need more oxygen, wake up a little bit. And so yawn is like, to just pull a little more oxygen in. They're also very catchy, in the sense that if you see somebody else do it, it's easy for you to do. That's probably a frontal lobe thing, where as you see somebody else respond that way, you think about what it feels to be tired as well. I realize it's fast, and then you yawn as well. More research is needed. Hiccups aren't on purpose. I don't think we have time for this. Maybe we do. No, we don't. Feel free to watch things on your own if you want to. Hiccups are inspirations that the timing's off and you end up smacking your respiratory system into itself. They're not life-threatening, they can be annoying. Everybody has different ways to get rid of it. The typical idea is just to kind of reset your breathing and your airflow in general. My personal favorite method of getting rid of hiccups, if you ever have hiccups, or sorry, if somebody else has hiccups, and they say, I have hiccups, You just look them dead in the eye and say, prove it. I don't think you're hiccuping, try it. And then they try to hiccup, and they can't, often. So there's always that option. But everything that's trying to cure hiccups, right? So drinking water really fast, or getting surprised, or trying to make yourself sneeze, or whatever else you do. All that's trying to do is you're trying to basically reset your breathing so you're not off kilter. Okay, with that, that's our breathing portion. Let me actually get my phone over here so I can watch the time, so I know I don't talk too long. We are on to the digestive system, which is basically this system here, right? Food comes in, food goes out, and a series of events happen between there. So that's where we're at. The digestive system, I should actually check that I'm recording. Yeah, I'm good. Hi. The digestive system is doing several things. The main one, right, is you're trying to absorb molecules into your bloodstream. You're trying to get the nutrients from food, and you want them inside your body. You want them inside your system. And inside, where your cells can actually get them. But to achieve that, you have several other steps that have to happen. You need to get food into your stomach or your GI system in general, right? You need to get food from outside into your GI tract. So you need to get food in. You need to then liberate the nutrient molecules. So you're gonna have something like an apple, right? That there's nutrients in it that you want, but they're tied up in the apple. You need to be able to tear that apart and get the pieces that you want in small enough pieces that you can absorb it. So you need to take food in, break it down, absorb those molecules that you need into your bloodstream. And then you also need to get rid of the indigestible bits. You need to be able to move them out so you don't clog the whole system up. These two people here, I don't know if you've ever heard of them. They're here just because I feel like we need more stories in our lives. William Beaumont was a physician, and in 18 something or other, he was up in Canada. This man, Alexis St. Martin, got in an accident where he ended up getting like a hole in his stomach. I believe it was a hunting accident. So he ends up with a hole in his stomach. William Beaumont treated him, but the hole stayed open. And then for the next like 12, 15 years, William Beaumont kept watching St. Martin, and basically St. Martin was fistulated, meaning he had a hole inside his digestive system. He was fine, he was healthy, but you could legitimately like look into his stomach. So what Beaumont would do would be he'd like, again, St. Martin must have been like pretty chill, because he'd like Beaumont would take little fluid out of his stomach and put it in little jars, and then put different foods in it and watch what happened, watch it break down. He also did this thing where he'd like get a piece of meat and tie it on a string and put it into St. Martin's stomach, and then every couple hours pull it out and see what was happening with it. Anyways, I don't think I will ever be that chill. I appreciate that for science you should do many things. I'm not sure that I'm that like, yeah, sure. But St. Martin lived to be like 80 something, like he lived a long time. And he was fine, but yeah, he always had just like an opening to the outside world. Anyways, all that's to say, the digestive system's interesting, and it's doing lots of different tasks, all to serve this. We need nutrients in, we need waste out. So the organs that are going to get this done fall into two big groups. It's called the gut, or the GI tract, or the gastrointestinal tract, or if you want to be fancy, the alimentary canal. So this is the tube that's mouth to anus. It's the tube inside of you. It's the big tube inside of you. It's going to digest food. it's going to be where you're actually absorbing nutrients through that lining into the blood. And this has the mouth, the pharynx, the esophagus, the stomach, small intestines, large intestines, anus. We describe as different organs, but they're all just that tube there, the whole tube there. Then there are a bunch of accessory organs, or things that help digestion. These are things like the teeth and the tongue and the gallbladder and a whole bunch of glands that are going to help service this GI tract. So here we have the whole picture, right? We've got the mouth, so we're going to just trace the tube here. We have the mouth, right? You can go down through the pharynx. We've got the esophagus we're coming in through. We're going to hit the stomach, right? From the stomach, we're going to hit the small intestines first, which they're longer, but they're smaller in diameter. We're going to hit the small intestines. We're then going to hit the large intestines. It's right here. Sorry, large intestines. And then the anus and oats. So that's the path of food. We have a couple helpful accessory organs. We've got things like the tongue. We've got a bunch of salivary glands that are going to be associated here. The pancreas is helpful. The liver and gallbladder are also going to be helpful. But yeah, that's where we are with the digestive system. So several things are going to happen here. I meant to have these show up one at a time. All right. Different terms. These are all basically just vocab words. Ingestion is the eating idea, getting it inside of you. Propulsion, this happens throughout the GI tract. But you need to move food through that gut, right? This is not gravity driven, which is good. You don't have to be standing up to be able to digest food. You can be lying down. You can actually, I don't know if you've ever tried it, but you can, like, if you're standing on your head, or if you have your head tipped over, you can still swallow, right? It's not gravity driven. You can move it against the force of gravity. So propulsion happens from two main reasons. There's swallowing, right? There's also peristalsis, and we're going to see this in a second. So ingestion, propulsion, important digestive processes. There's also mechanical breakdown. This is when you basically have your food, your apple, your cracker, your chip, whatever it is you're eating, and you kind of hit at it with a hammer for a while to physically crunch it into little bits. So this is going to be something like chewing, turning food in the stomach. So if you have, I realize this was the lungs just a minute ago, but now this is the stomach. If you have food inside the stomach and you then churn, but you're just like, and basically just crunch it down inside the stomach, right? That's churning. Segmentation, we'll see again when we look up, we'll see it here. So mechanical breakdown is that we're actually crunching it down physically by hitting it with a hammer, basically. Digestion is when you're pulling food apart chemically. So you're going to be using typically enzymes that are going to be breaking down some complicated food molecule into little bits, right? So you've got your apple and you hit it with a hammer. You now have small pieces of apple. But if you put your apple in with, say, amylase, you're going to have certain carbohydrates get dissolved down digested down by the enzyme. Absorption then is when you get those little fragments that you've made. They're inside the GI tract. You pull those across. Typically into the blood, you can also pull across into the lymph. So you're pulling across the tube into the inside of the body. And then defecation is just getting rid of the stuff you can't digest in the form of pieces. So two terms, and you just need the picture to see it. Peristalsis is this thing, the mental picture I have is like, you know how you see videos of snakes swallowing eggs? You know, like see it move along? That's the idea here. It's where the oh, excuse me. Sorry, I'm talking about yawning. Man, messed me up. Where you're going to be pushing. It's called a bolus. You're going to be pushing a blob of food on. So you basically have the the um, the first part contract, and the next part relax. And so then you contract this next part, and you relax this part, and it gets pushed along. It's moved distally along the track. It's being pushed forwards or down through the track, right? So contract, this moves forward kind of bit. Contract, moves forward. Contract, move forward. So as you swallow, this bolus of food should be pushed by these muscles the whole way down. And then you could swallow another one and keep having it come down. That's peristalsis. Segmentation is so peristalsis. The idea is that you're just propelling this food, this bolus, this material through. Segmentation, the idea is to mix stuff up, and what this happens is it's got backwards and forwards motion, where you're going to contract, right? So these are all contract, right? And you have different food and digestive juices here, right? Contract, contract, contract. But then you contract in different spots, so you mix stuff together. Boom, so right? These were here, then you contracted right here, but relaxed this, but contracted there. These portions mix. And then you go back and forth. And the idea is to, my balloon is not perfect here, but churning in like the stomach is like all over the place. But if you have segmentation happening, I've got stuff here, I've got stuff here, I contract right here, and then contract here, and then contract here, then contract here. I'm sloshing it back and forth to mix it. Some propulsion can occur. You can keep moving things forwards a little bit. Just like with peristalsis, a little bit of mixing can happen. But the general idea is to just keep moving it forward. Alright. Hopefully so far so good. I realize I like pause in actual class more, but here I'm not pausing because you have the pause button on your computer. So here's this diagram of things that are happening in different portions. Right, so we have the tube here, the gut, right, and then this is like inside the body. And they're color coded, right? So ingestion's happening here. Mechanical breakdown is happening a couple places. Here it's in blue. Mechanical breakdown is happening in the mouth. It's happening in the stomach. It's also happening in the small intestines, right? So we see this mechanical breakdown happen several places. Propulsion is happening the whole way through, right? So propulsion from when material enters the mouth to when it is removed from the body via the anus. This is getting propelled the whole way through. Digestion is happening mostly in the small intestines. There's a tiny bit. It happens in other places, but mostly it's happening here. The stomach's not really doing that much digestion. We'll get to this later. Absorption is happening in the small intestines, some of the large intestines, but honestly, by the time you get there, mostly you're just pulling back water. Yeah, so you're absorbing here, and then defecation is just an anus thing. So, when we're looking at the just the actual cells, all the digestive organs, so ignoring the accessory organs for a minute, all the digestive organs have 4 basic layers that are called tunics. I realize like a tunic in just English is you're talking about like this shirt-like thing, but for us in anatomy, this tunic is just going to be a layer. Mucosa is because this whole GI tract is technically all open to the outside. I realize like somewhere here by the time you get to the colon, it's not really open to the outside, but it still is because it's not inside the body, it's open. So these are all going to be lined with mucous membranes. So this tunic layer that's in there is going to be the mucosa. It's going to be secreting mucus. It's going to be secreting digestive enzymes. It worries about hormones. It's also going to, so it's going to be dumping stuff out. It's also going to be pulling stuff back in. It's where the end products of digestion are absorbed across. And it's also helping against like infectious diseases. Mucosa is a very important layer. It's going to be keeping random pathogens out of you. It's going to be putting the bits that you need to actually digest food appropriately, and then pulling those products back into the body. The submucosa is basically connective tissue. It's going to have blood and lymphatic vesicles. This is really important because you need, once you pull nutrients through that mucosa layer, you need to be able to have some place to hand this stuff to, and the blood is a really good place to hand this to. It's also, so it's got this connective tissue, it's got a lot of elasticity to it, which is nice because your GI system is going to expand, like your stomach especially is a really good example. It's going to expand, and you need it to be able to regain its original shape even after you've moved food through it. Excuse me. Sorry, so we've gone from inside to out, right? So we've got the mucosa layer, right? And we've got the submucosa. And then we've got the muscular layer, muscularis externa. It's the part that you're actually going to be using for segmentation and peristalsis. It has two different layers. It's got a layer that goes around like this, and then the layer that runs long ways. It also doesn't have a number of sphincters, which I realize people for some reason only talk about anal sphincters or think about them. But they're just going to be muscle bits that are able to contract down and basically act as gates. We'll see those later. And then the outside, the serosa, is nice. It's the outside layer, it's there. So when we're looking at this is what we're looking at. So we've got here at the very center, this is where you actually put food, right? We've got all this mucosa layer, right? We've got some glands going on. We've got this nice set of cells. So far, so good. Great. Next, and sorry, we see the glands. So the glands count as being in the mucosa layer, even though they're like pushed up into the submucosa. But they're continuous. They're continuous with this mucus layer. Okay, so we've got a submucosa, and you can see we've got a whole bunch of things going on. We've got a whole bunch of vessels, right? So we've got this also is innervated. So we've got nerves here. We have quite a bit of blood. We also have lymphatic vessels. So that's great. So as we push, pull is a better word. As we pull nutrients across, we'll end up here. Then we have this muscular layer. This is, oh sorry, I don't know, I'm super yawny today. This is where we have this smooth muscle tissue running both directions, running around in the loop, as well as running long ways. And then we finally, just get to cover the whole system up. Great. Oh, and next we're going to look at, it's kind of pretty here. This, you'll see this is the stomach, right? Moving on to the intestines. What this is stained for is it's stained for neurons. It's stained for the nervous system. The enteric nervous system is this thing that the GI tract has its own nervous system. People call it the gut brain, called the enteric nervous system. It's got so many neurons. It's got more neurons than the spinal cord has. And it doesn't get the press it deserves. These neurons, they're nervous tissue, right? They're neurons. They're going to be this system has neurons that are going to be talking to each other. They're communicating with themselves. The big point of what they're going to do is control how fast things move through the system. And this nervous system, this enteric nervous system, has what they're called reflex arcs, and they come in both short and long. So the short reflexes are going to be these neurons that are responding to stimulation inside the GI tract. So as there's pressure changes or pH changes, or the pressure gets lower, or something that's happening right there, these short reflexes respond to that. The long reflexes can listen to things happening right there. Suddenly there's more pressure, suddenly there's a lot more lipids, suddenly there's a lot more protein, suddenly the pH changed, that kind of thing. Or they can also respond to stimuli that arises outside of the gut. So things like, I'm really nervous. And you might have noticed, right, if you're really nervous, your digestion slows down often, right? Like, things just don't work so well. They can respond to a whole bunch of stimuli outside that. The autonomic nervous system is going to play a huge role in this. The parasympathetic system of the autonomic nervous system is going to encourage digestion, right? Whereas the sympathetic system is going to kind of turn digestion off a little bit. So here's the idea. We've got the GI wall, right? We've got, here we're into the lumen. This is like where you actually put food, right? Short reflexes are going to be paying attention to chemicals, to the osmotic concerns, right? How much water, how much salt, whatever. And then also mechanical stimulation. And they're going to be telling the smooth muscles and the glands of the GI system what to do, right? So secrete more, stop secreting something, contract more, stop contracting, that kind of thing. External stimuli are going to feed into this via the central nervous system through the long reflexes. And information here is also going to the central nervous system. The central nervous system gets to know what's going on in the GI tract. So there we are. People don't realize how many neurons the gut has to deal with. It's a lot. Alright. How are we doing on time? We're not going to finish everything, but that's okay because we have plenty of time in the class as a whole and plenty of days. Let's see. We'll get through at least some of these. Okay. So, if you're going to, overall, if you're going to, this is the take-home message of this last little bit, if you're going to control digestive activity, you control it by a whole bunch of both mechanical, like physical, as well as chemical stimuli. So, you've got receptors that are located throughout the GI system. They're embedded in the walls of the GI tract. And they're going to respond to things like stretch. So as your stomach gets more full, you've got receptors that can notice that, right? If the osmolarity changes, they can notice that. If the pH changes, they can notice that. If there are things like lipids, they can notice that. They can realize, like, oh hey, a moment ago there weren't lipids, now there are lipids. Something changed. Once the GI system notices something, what is changed is the smooth muscle activity, right? Do I contract? Do I not contract? Do I speed up contraction? Do I slow down contraction? And glands. Do I secrete digestive juices? That's a hard phrase to say. Or hormones or things like that. Yeah. Okay. So now on to the anatomy part. This I'm convinced you're solved with. The mouth is hereish, and it's where food gets chewed. And you mix it with some enzymes in your saliva, you start digestion, and the swallowing process happens. You don't have to have a mouth for digestion for digestive system to function, right? So like, if you were to swallow things whole and not chew them, you could still get nutrients out. If you were to be, say, fed through a tube, that could happen. That could work as well. But the mouth, for normal situations, is very helpful. It's going to get food broken down into smaller pieces. You're going to be able to get more nutrients out faster, not swallowing things whole. The saliva also starts digestion. It's going to have the saliva is going to have some enzymes in it, some other things that are going to help start breaking down different portions of food. Some associated organs here are going to be the mouth. So you've got the tongue, salivary glands, and teeth. The mouth is going to be called the oral or buccal cavity. You know where it is. The oral orifice is the hole. Yeah. On the inside of your mouth, you've got stratified squamous epithelial tissue, right? So lots of layers, because you're forever chewing and putting things in your mouth, and bits of that tissue get sloughed off, right? So you want multiple layers. They're pretty tough cells, actually. And then if you go around and, I guess, poke your face, your gums, your hard palate, parts of your tongue have keratin in them as well to make them extra tough. Your lips and cheeks are made of muscles. Yeah. You've got oral vestibules, which if you want to like pack food in because you don't want to swallow it because you're like 2 or something, go for it. The oral cavity proper is the part that's back behind your teeth and gums, that your inside part of your mouth. And then, I don't know if this is creepy, but the part that attaches your lip to your gum is called your frenulum, or labial frenulum, so frenulum of the lip. Yeah. So, yeah, lip to gum. This, you probably, as a child, it probably was bigger, but you probably fell, and it probably got broken, and you probably bled, and now it's probably a little bit looser. That's typical to have happen. But here we are. So far, so good. Oh, and the hanging down bit part in the back of your mouth is called the uvula. Right there. Here we are. So you've got the frenulum holding your lips to your gums. You also have the one with your tongue. It's called the lingual frenulum. Again, not a huge deal, though they're often broken on accident as people age, they fall and trip. Sometimes infants have a frenulum that's like too tight, like holds their tongue down too much, and this can be a problem for nursing. It's called being tongue-tied. And doctors honestly just go with a pair of scissors and will snip it to free the tongue a little bit. Yeah. So far, so good. So the tongue is there. It's surprisingly large. So you see part of it when you see your tongue, but there is a lot of tongue. It is very big. Tongue, again, is not necessary to, survive. You can do it without having a tongue. But it's helpful. It's a whole bunch of skeletal muscle. So most of the GI system, you're expecting smooth muscle, but the tongue is an accessory organ here. It's a bunch of skeletal muscle that laces different ways. It's going to move food around while you chew. It's going to be able to glob food together in what's called a bolus, which is food and saliva. It's going to be able to set off swallowing. This is important. It does taste. So you also have taste buds, some other portions of your mouth as well, but your tongue is where most of them are. And it's going to be hugely important for speech. There are intrinsic muscles to the tongue that are inside that can change the shape of the tongue, so you can do things like, or like, right? That kind of thing. And then you've got extrinsic muscles that are going to change where your tongue is in relation to everything else. And then the lingual frenulum, is how your tongue is attached to the floor of the mouth. So there's the tongue. That's good. We're going to get through mumps, and then we're done for today. Okay. we've got, okay, so tongue, yeah. We've got salivary glands. They produce saliva. The idea for that is to clean out the mouth. It's also going to dissolve food chemicals for taste. Depending on what the plague situation is next semester, can reduce sensation, or you can just try this at home. If you get like a cotton ball or a whole wad of paper towels and you dry off your tongue, and then you try to taste things, you can't. If your tongue is dry and you're trying to put food on it to taste it, you can't. You have to have those food chemicals dissolved to actually be able to taste them. So yeah, saliva is going to be able to dissolve chemicals for taste. It's also going to help you swallow. So if you're ever super bored, you can play the game of eat 4 saltine crackers back to back and then try to whistle, right? If you suddenly run out of saliva because you've been eating too many crackers too fast, it becomes really hard to do lots of different things. Saliva is also going to help break down starch with the enzyme amylase. So it's not going to be worrying about breaking down like lipids or anything yet, but it will break down starches. And so we've got a lot of things going on here. Note there are several different glands, right? We've got a gland here, we've got a gland here, we've got a gland here, right? Lots of things going on, lots of muscle bits, and here we are in our mouth, and there's our teeth. When you look at this gland here, the parotid gland, it's important, all's well. If that gets inflamed, typically by this virus, it's called mumps. It's a problem. It's very spreadable via saliva. So if, say, you drink out of a cup, and then you have mumps, and then somebody else drinks out of the same cup, they are going to get mumps. This is why vaccines exist. Please be vaccinated for mumps. It typically in children is bad but not life-threatening, though it certainly can be. In some cases, it can get very scary. It hurts to swallow. It hurts to chew. Sometimes there are some really nasty high fevers. Everything hurts, and you feel terrible, and your face chipmunk cheeks out. In children, it's scary, can be life-threatening, but not in general isn't. It's not like polio. Again, don't get it though. Oh my gosh, because it's very infectious, and it also can cause very severe complications. The group that causes the worst complications to is if adult males get it. Often it for some reason infects the testes as well. So you get mumps. So this virus comes in, you get as mumps, but it also attacks the testes, and people go sterile, like they're not able to reproduce. It's a thing. Don't get mumps. So get a vaccine for mumps. So yay for that. That's all we've got time for today. On Thursday we'll pick back up with teeth. And yeah, hopefully that's good. I'll see you in lab, or you'll have the online lab, and that should be great. Thanks.